Welcome and hello. This is a video tutorial in the FHWA hydraulic toolbox. In this lesson, I'm going to be talking about bridge scour calculator, specifically Pier Scour. All right, so if I bring up an image from the user's manual on Pier Scour, what we have is a bridge deck, left and right abutments, and then a couple piers here. Here's a left pier, here's a right pier, and the bridge scour is the removal of material through erosion adjacent to the pier itself. Pier scour is a type of local scour that occurs around a bridge pier. When water flows past a pier, it accelerates and causes turbulence, which removes the sediment from around the pier. This image here is on page 72 of the user's manual. You can download the user's manual from the hydraulic toolbox if you go up to the help menu, and then this first option here, hydraulic toolbox user's manual, that should open up a PDF document for you. The other PDF I'm going to be referencing in this video is Hydraulic Engineering Circular number 18, Evaluating Scour at Bridges. And then you can download this PDF file. I'll leave a link to where you can find that in the description of this video. All right, so where the Pier Scour calculator is within the hydraulic toolbox, what you want to do is go to your project, add bridge scour analysis, double click on that, and then the Pier Scour is right here, local scour at piers. Go ahead and check that checkbox on so it's checked, and then here is the interface. We have the number of piers and then some of the pier data, like the name, the Pier Scour parameters, the Pier Scour reference point, and then options to duplicate or delete that pier. So mostly what we'll be talking about in this lesson is the options within this define button, where we decide the computation method, input the input parameters, and then look at the results down below. Okay, let me just back out real quick and mention that the bridge scour analysis can be added a few different ways. We can click on the button right here, new bridge scour analysis. I'm going to go ahead and delete that. I've already done an introduction on bridge scour analysis in lesson 19. So we're on to number 23 now. So we don't need to talk about all those details again. But what I do need to do is add a .prj HEC-RAS project file. So I'm going to click on this checkbox, click on import, and then click on the browse button and navigate to my .prj HEC-RAS project file. So I'm going to do that. And then what it has loaded is the approach cross section, which I have defined at River Station 600, and then the upstream bridge cross section, which I have defined at River Station 400, and then finally the actual bridge structure itself, which is right here. Once the bridge is selected, it has my three piers identified. One is at cross section station 30, cross section station 75, and cross section station 120. We're not dealing with abutments right now, so I'll leave that as it is. But those three piers should be reading in from my HEC-RAS data. Here's the geometric data editor. What I've already created and demonstrated back in lesson 20, if you're curious, is created this model and explained it in more detail. But for now, here is my bridge centered at River Station 300. This is the plan view right here. If I click on bridge, you can actually see the front view where we have the bridge deck, the left and right abutments, and then the three piers at cross section 30, 75, and 120. I've already ran a simulation with two different flow profiles. So if I open up the results here for the cross section, what you're seeing here is the flow profile for 7,000 CFS, a steady state flow. Here's 1 and 3, which I'm calling left and right overbank piers, are 3 feet deep. And then pier 2, this middle pier, is 13 feet deep. That's the one in the main channel. Okay, so we can come back to the HEC-RAS data later if we need to. For now, let's just go to click OK for the input data. I'm going to create a scenario. It starts me off with one scenario here. This time I'm just going to say 7,000 CFS and then tab off. So that's my one and only scenario. It looks like it's already checked on some of these other scour methods. So I'm going to uncheck these here. Local scour at piers. This is the one I want to leave checked on. And already it's identified the three different piers when I uploaded that HEC-RAS file. There's Pier 1, the centerline station at Pier 1. I thought it would know this actually. That is at 30 feet. And then Pier 2, that is 75 feet. This is the cross section station now. And then Pier 3, I'm going to put that at 120 feet. Pier geometry, I'm going to click on define. And then what I have is a dialog box where I need to specify the width and elevation. So for Pier 1, I'm going to say 2 different points, tab off. The pier width is 4 feet at the top and the bottom. The top is 250. That's the bottom chord of the bridge deck. And then the other elevation is the soil, which is at 240. So click OK. Pier 2, I'll click define. This is also 4. Okay, so it looks like the data was already in here. 250, that's correct. Instead of 240, this is going to be 230. And okay, somehow this number got deleted. That's supposed to be 75. Oops, this one is supposed to be 30. And then down here, this is 120. I'm going to define the geometry for Pier 3 now. That is correct. Actually, no, this needs to be 240. And okay, defining the Pier Scour parameters, I'm going to do that last because it's the most involved with the equations and everything. But before we do that, I'm going to set the Pier Scour reference point. Instead of using FHWA, I'm going to be using local. That's going to be true for all 3 piers. What that's referring to, if I go back to the user's manual to this diagram, this left pier is using the local reference where the scour depth is a function of the original soil elevation compared to the scoured soil elevation, whereas this right pier is using the FHWA reference where this distance is the difference between the scour and the FHWA. That's a vertical elevation. Okay. Once all of that is done, and you switch this to local, you can click on the plot preview button down here at the bottom. Oops. Okay, so something got goofed up. 1 second. Let me close this. Yeah, some of these values are not saving, so I want this to be local. Pier 1 is supposed to be at 30, Pier 2 at 75, Pier 3 at 120. Let me just click OK and see if that's saved. So I'll open up the bridge scour analysis once again. Okay, I got it fixed. Now if I click on plot preview, what you see is the cross section. I've got the left overbank, main channel, right overbank, and then my 3 piers that have been sketched in here, approximately 10 feet, 20 feet, and 10 feet tall for left, center, and right, respectively. The bridge deck would be across the top, but this general shape, as far as the pier location, width, and position, as well as the cross section, should be similar to what we saw in HEC-RAS when we clicked on the bridge right here. Okay. Again, the water depth is going to be about 243, so the water depth is going to be right about here, and we can check out the actual depth values and flow rates if necessary. So I'll close that. Next, it's time to define the Pier Scour parameters. So here on Pier 2, this is the middle pier, Pier 2, for the main channel. I'll click this Define button right here. And now the first question we need to ask is which computation method we're going to be using. The options here are Complex Pier, HEC-18, Florida DOT, Coarse bed, and cohesive material. So whichever option you select, you're going to have to provide a number of input parameters, and then you'll see the results appear down below once the input parameters have been entered correctly. I'm here in the user's manual, page 82, section 15.5.1. This is where we start the discussion of the different bridge scour calculators, specifically the Pier Scour. So the first method here that's mentioned is the HEC-18 method. Here is the equation. It talks about the input parameters and the results. This equation is described in more detail in that Hydraulic Engineering Circular Document 18, equation 7.1. We'll take a look at that in just a little bit. Further down, we have the next method, Florida Department of Transportation method, with a similar equation for Y sub S, that is the scour depth at the pier. There's 3 different options there based on the velocity and the critical velocity. Next one down is complex pier method. So this figure is something we'll return to once we talk about that method. Also in the Hydraulic Engineering Circular number 18, chapter 7 is where it talks about Pier Scour if you wanted to really dig deep and follow along with the actual numbers. So this is page 167 for me. If you scroll down, we start getting a discussion of the different methods. Here's the HEC-18 Pier Scour equation. In fact, this is where we're going to start. So equation 7.1, Y sub S, this is what calculates the Pier Scour depth. Down here, we have the actual parameters listed out. Unlike the user's manual, the HEC documentation is usually a little bit more thorough and complete and easy to follow, especially if you're a first timer and like to have everything defined like me. All right, so Y sub 1, this is the flow depth directly upstream of the pier. 2, that's a constant. K1, 2, and 3 are all constants. These are correction factors based on the pier nose shape, the angle of attack, and the bed condition. So we'll be scrolling down a little bit further to get those numbers. In fact, let's do that now. So here are the different shapes available. A through E, we have square nose, round nose, cylindrical, sharp nose, and then a group of cylinders. Based on the shape, you select A through E in this table 7.1. Let me scroll up. It gives a K1 equivalent. So you don't need to select the K1, you just select the shape. Let's go to the calculator. The shape is the first selection we need to make. Here are those same 5 options: square nose, round nose, circular, and so on. So let's just go with round nose. That will compute a K1 value of 1.0. Okay. The next parameter we need to input is the bed condition. So that's K3. Here are the options. There's clear water scour, there is plain bed and anti-dune flow, small dunes, and then medium dunes and large dunes. Based on the dune size you provide, it tells you this is between 10 feet and 30 feet for the dune height. I'm just going to use clear water scour. So clear water scour defines the K3 variable. So if we scroll down, K3 here would be 1.1 for clear water scour. Back to our input data. The depth upstream of the pier, I'm going to say, is 13 feet because for a 7,000 CFS scenario, that just happens to be what the depth is. And then velocity upstream of the pier. You know what? Let's go ahead and check HEC-RAS for the actual upstream depth for this flow scenario, this profile of 7,000 CFS, as well as the velocity upstream. So back to our HEC-RAS results and click on View Profile Summary Table. This particular profile is for 7,000 CFS, and the cross-section 600, this River Station 600 cross-section is the upstream cross-section. So velocity in the channel is 8.3 feet per second. And if I wanted to know the channel depth, I'm not seeing that as a column here, but I can go Options, Define Channel, give me a new column here. I'm going to search for depth, and then scroll down here. I'm looking for depth in the main channel, hydraulic depth and channel right here. So double click. That is now my column 11. So click OK, and 11.06 feet. Okay, so I thought it was 13. Good thing I checked. It's 11.06 and 8.38. 11.06, and then the next field down, 8.38. All right. The width of the pier is 4 feet. That's just based on the geometry. The length of the pier is 100 feet because that's the width of the road. Probably a little bit wider than it needs to be, but and then angle of attack, I'll leave that at 0. That reference is the angle that the water attacks the pier. So if it's straight on 0 degrees, that affects K2, that constant parameter, which we saw in this table right here. K2, if the angle is 0, then the K2 value is 1. And then if the angle is more than 0, that K2 value depends on the L divided by A, where A is the width of the pier and L is the length of the pier. Okay, so I'll just leave that at 0. Now we have some results down below here. The result I'm going to be looking at the most is this scour depth right here, 8.86. But there are a number of other calculations, such as our values for K1, K2, and K3. L divided by A wasn't used because we have an angle of attack of 0, and we have the Froude number. And yeah, the scour depth of 8.86 is what we're looking at, as well as some scour hole parameters. So if we look at 8.86, I click close, and then I click on this plot preview button. We now have 8.86 feet of scour that you see outlined by this red line right here. Pier scour, and I should also see that 8.86 if I click on the bridge scour summary table for pier number 2, 8.86, total of 8.86 feet. Okay, so of course that specific scour depth does depend on the parameters, and if I click on define again and change some of the values, say for instance the pier width was only 3 feet, I changed 4 to a 3, and then scroll down. Now the scour depth is only 7.2 feet, so that's less. That makes sense. And if, for instance, the upstream velocity wasn't 8.83 feet per second, if it was less, something like 2 feet per second, I tab off. That affects the Froude number, of course. That's now less, still subcritical, and the scour depth is now just below 4 feet. Okay. So that's how that works on the HEC-18 method for Pier Scour. I'm going to click OK. I'm going to now pick on a different pier. How about Pier 1? And click on the Define button. And now let's check out the Florida DOT method for Pier Scour. In the documentation, this is the HEC-18 document. I want to go to page 172, or the bottom of page 171, Florida DOT Pier Scour methodology. If we scroll down, we are now solving for this y sub s value. That's the depth of the scour, of the pier scour. There's actually three equations you're seeing. Let me zoom out. 7.5, 7.6, and 7.7 all solve for that y sub s, the depth of the pier scour. And the equation of those three that you're going to use depends on the velocity v1 compared to the critical velocity v sub c. So v1 is the upstream velocity. Let's see, it should say that right here, the mean velocity of the flow directly upstream of the pier. And then v sub c is the critical velocity right here, which is based on the d50 and defined below. So equation 7.12 defines the v sub c. Here is your equation for that. All of these equations are sort of taking care of themselves behind the scenes in the calculator though, but it's nice to know where those equations come from so you can check the actual numbers if you're interested. Let's go ahead and just put in some numbers and see what happens. So pier shape, round nose, these are the same shapes as before. It looks like we just have square nose, round nose, and circular as our options. And then the depth upstream of Pier 1. Now, Pier 1 is the left overbank, so if I wanted to actually get a number here, I'd have to go back to View and then Profile Summary Table. I need to add a column to figure out the depth and velocity. All right, so let's type in depth, and then I'm looking for the left overbank, hydraulic depth in the left overbank, okay? And then velocity, let me search for a velocity. Average velocity in the left overbank is columns 11 and 12, so that is right here. And then this cross-section 600 is the approach cross-section, so 3.37 and 2.71. Those are the two numbers I want to use for the left overbank. And again, this entire profile PF2 is for 7,000 CFS, which is the same scenario that I'm using in the hydraulic calculator. So I'll close that. Back to the hydraulic calculator. Upstream depth of pier 3.37, and then the velocity upstream is 2.71 feet per second. The width of the pier, that hasn't changed, still 4 feet. Length of the pier is 100, and then attack angle, I'll leave that at 0, and then the D50 value, I'll just make something up. I'll say 0.2 millimeters. So when I click on tab, I now get my results. We have different results, of course, because these are different calculations, different equations. We have values for F1, 2, and 3 instead of K1, 2, and 3. Again, those are all discussed in the HEC-18 document. We have a shape factor, critical velocity. Critical velocity is important because remember that helps determine which equation we want to use for our scour depth based on this velocity of V1. Anyway, scour depth is right down here, 4.23 feet, which makes sense. It wouldn't be quite as deep as the main channel here, which was originally something like 8 before we changed some of the input parameters. So 4.23, let's go ahead and take a look at that on the plot. I'll click on Plot Preview. Here is the 4.23 feet of pier scour and our pier in the left embankment. All right, let's go ahead and just modify a couple input values here. So how about instead of a velocity of 2.71, I just decrease it to 1, and that's in units of feet per second. So the scour depth is going to change from 4.23 feet. Click the tab button. Now we're down to 3.18 feet. So less pier scour with lower velocities. That makes sense. If the angle of attack is different, so instead of 0, I changed it to how about 15 degrees, then the scour depth increases from 3.18 feet up to 8.56 feet. So it looks like the scour depth is rather sensitive to that angle of attack. And then the pier length, if it wasn't quite as large, maybe how about just 30 feet? Let's see what happens. 8.56, 5.55. Okay. So it takes a little bit of manipulation to figure out which is the best pier design. And then once you have the design, it's just plug and chug to figure out what that scour depth would be. As before, we have some numbers for the scour hole dimensions. All right, so that is the Florida DOT computation method for Pier Scour. I'll click OK. And then for Pier 3, let's go ahead and use this pier now for the complex pier computation method. Complex piers are a combination of a foundation, pile groups, pile caps, and pier stems, either exposed by design or exposed by the scour process. I'm going to bring up the HEC document 18 here. This is on page 178, figure 7.5. And this shows that there are actually three different components to the scour depth when using this complex pier method. The complex pier method extends standard pier scour equations and generally gives conservative results based on superposition, which is where the scour is calculated separately for each exposed component and then combined to estimate a total scour depth. So that's what we're doing here. We have the combined image or structure over here to the left, and then that equals the sum of these three parts. See the little plus symbol is what it's trying to say. We have the pier stem, the pile cap, and then the pile group. So we're going to have a section in the input for each of these three different components for both input, results, and then finally a total scour depth. That's what this equation is trying to tell us right here. We have a number of different input parameters, so this will be fun. Here is our summation for the total scour, 7.22, and then the three different components that are defined right down here. If you keep scrolling, you get more equations. So let's just go ahead and go back to the calculator and make up some numbers here based on our actual HEC-RAS data. Thankfully, a lot of these parameters have already been defined, so we'll just go with the pier shape of round nose, bed condition, clear water, bed material. Our options here is sand or gravel. Let's just go with, how about sand? After that, angle of attack, we'll say 0 degrees, depth of upstream pier, and velocity of upstream pier. We just looked this up. Remember, we're on Pier 3 now, so this is the right overbank. It's actually going to have the exact same depth and upstream velocity as Pier 1, which was 3.37 feet for the depth, and then the velocity was 2.71 feet per second. Down below, we have the input parameters for the pier stem, pile cap or footing parameters, and then bed material parameters. And then also we should have a group for the pile group parameters, which will appear in just a moment. Okay, so let's get started here on the pier stem parameters. Distance between front edge of pile cap or footing and the pier, which is dimension F. So if you're ever unsure what it's talking about as far as these dimensions go, you can go back and reference that figure 7.5. F right here is this distance right here. So it's basically from the front edge of the pier to the front edge of the pile cap. So let's just throw a number in there. I'll say 4 feet. And then below that, we have the pier width, that's 4 feet, and then the pier length, that's 100 feet. Okay, if I tab off of that, we can now enter data for the pile cap footing parameters. Initial height of the pile cap above the bed, H sub 0. So H sub 0, if we go back to this figure right here, here is H sub 0. I'm going to say this is 0, meaning that the pile cap is resting directly on the bed. So go back here, we'll just leave that at 0. Okay, height of the pile cap, that's calculated. Thickness of the pile cap or footing, I'll just say 3 feet. That's variable T. So the thickness of the pile cap, T, is this dimension right here. And then finally, the pile cap width, I'll say, is 12 feet wide. So with that data entered, I now have my pile group parameters, which have appeared. So the individual pile width, again, I'm just making up numbers here. 2, spacing between the columns of the piles, I'll say that is 3 feet. Number of rows and number of columns. So rows is perpendicular to the direction of flow. I'll say 2. And then the number of columns, I'll say, is 10. All right, the last input I need to provide is the D50 value. I'll say that's 0.2 millimeters. And then when I tab off, scroll down, here are my results. There's lots of results. There's a section here for pier stem parameters, pile cap parameters, and then pile group parameters. Ultimately, the total scour is 8.04 feet, which is similar to what we had for Pier 2, which was in the main channel. But remember, we're in the overbank now. The individual pier depths are calculated as 4.66, 2.75, and 0.64. those three should add up to 8.04 or 8.05. I think there may be a rounding error, but close enough. All right. And then as before, we have scour hole dimensions as well. So that's how that works. Again, we could change some of the values to reduce the scour depth or increase the scour depth or just see how that changes. What I've been doing before is decreasing the velocity. So instead of 2.71, let's just say it's 1, and that's units of feet per second. That decreased the scour depth quite a bit, actually. We're down to 3.34 feet, and that's the total scour depth, which would be the sum of 1.80, 1.12, and 0.42. All right, the last two computation methods are called coarse bed and cohesive materials. As you may imagine, they are for coarse aggregate, sands and gravels, and cohesive materials. If you click on them, you have to input parameters and then get your results. In the HEC 18 document, that starts in section 7.11 on page 203, Pier Scour in coarse bed materials. And then the next page down, we have the equations and explanation for Pier Scour in cohesive materials. So more equations, more data to look through. I don't think me going through another two examples here is going to change anything. So hopefully this lesson gave you a pretty good idea and head start on how to get going with calculating Pier Scour, which is a component of the bridge scour calculator in the FHWA hydraulic toolbox.